We present ScatterUQ, an interactive scatter plot to visualize machine learning neural network uncertainty by comparing the proximities of test samples with training data. Deep neural network machine learning models are becoming increasingly popular for multi-class classification, but the distribution of data used to train ML models is often different than the distribution of real data that models encounter. For example, a model could be trained on fashion MNIST to recognize articles of clothing. Here, the articles of clothing would be considered in distribution. But in the wild, the model could encounter handwritten digits, cats, dogs, and all other kinds of images that the model has never seen before, and that would be considered out of distribution. And when models encounter data in the wild that is confusing or dissimilar from the training data, it's important to quantify their uncertainty to help end users make appropriate decisions and to maintain end user trust. Otherwise, end users may blindly trust the model, make inappropriate decisions, or lose trust in the model altogether. In our paper, we utilize a distance-aware prototypical neural network architecture. The neural network projects input into an arbitrarily high-dimensional final embedding space and learns to cluster samples from the same class close together while also separating the different classes. The prototype for a class is the average of several labeled training examples, and over iterative training episodes, the model learns the class separations by updating its weights via gradient descent. We extended this architecture to provide extra uncertainty quantification context. In addition to outputting calibrated class probabilities, we also output an out-of-distribution or OOD score. The class probabilities are calculated as the softmax of the input's distance from various prototypes, and basically the closer an input is to a prototype, the more likely the model thinks it belongs to that class. So here the input image lands closest to the ankle boot prototype, so the model will think that it is most likely an ankle boot, less likely a sandal, and least likely a shirt. The distances in the embedding space are also used to detect OOD examples. We define an outlier score based on the distance to the closest prototype using the Mahalanobis distance. In this case, when the input lands close to the prototypes and their Mahalanobis distance is small, the model thinks that the input is in distribution. However, when the distance is large, for example, in this case, when the input image lands far away from all the prototypes, the model thinks the input is most likely to be OOD. And at test time, we compare the distance of a new point to the closest prototype to this distribution to compute the probability that an in-distribution example is closer than the test point, which provides an interpretable OOD score that does not rely on a separate OOD dataset. For our demo of ScatterUQ, we trained a ProtoNet model on fashion MNIST. There are 10 classes in the dataset, and we used a 10-dimensional embedding space. But because we and many end users cannot visualize in 10 dimensions, we decided to use a dimensionality reduction technique called principal component analysis to visualize the data as a 2D scatter plot. And we then tested the model on inputs from fashion MNIST as well as the regular MNIST test sets. ScatterUQ uses two confidence sliders to determine which use case a test sample belongs to. The outlier tolerance slider filters out test samples that may be OOD. If the outlier score of a sample is too high, then the sample is reclassified as other. The second slider controls the class confidence threshold. If the class confidence scores of a sample are all lower than the class confidence threshold, then the sample is reclassified as other. This is the basic ScatterUQ user interface. The left sidebar displays the test image, predicted class, class confidence scores, and outlier score. In the scatter plot, the test input is the large dot here, and surrounding the test input are various other training examples that the model saw during training. The black dot here is the class prototype. The confidence contours are generated after dimensionality reduction using D3 contour and the marching squares algorithm to generate nominal but not entirely accurate contours. When the user hovers over different training examples, the right sidebar updates to display the input image and scores. There are also some dimensionality reduction metrics for advanced users that I will talk about later. Here the model is confident that this test sample is an ankle boot because it's nearby the other ankle boots from training. By hovering over different points, the user can compare the test sample with training examples using the two sidebars. An end user may ask the question, why is the model highly confident about its prediction? This is because the sample lands close to one prototype and looks like data from this class from training. ML consumers can more confidently decide a downstream course of action, and engineers may not need to take any action since the model is behaving as expected. The second use case is shown here, where the model thinks this test sample is in distribution, but is unsure of whether it belongs to the shirt or t-shirt class. ScatterUQ displays a local PCA plot of the test samples of the test sample and both the shirt and t-shirt training examples, allowing the user to compare the test sample with the training examples from the two classes to make a final decision. An end user may ask, why is the model confused about which class the sample belongs to? This is because the sample lands in between the two prototypes and looks like data from both classes. Consumers know to be careful about using the class predictions, and ML engineers know they may need to add additional training data to fine-tune the model or to refactor their labels. The third use case is shown here, where the model correctly believes that the test sample, which is a digit 6 from MNIST, is OOD from its fashion MNIST training set. ScatterUQ displays a local PCA plot of the test sample and the training examples from the nearest class sandals. The user can compare the test sample with those training examples to determine if the sample is truly out of distribution. The end user may ask, why does the model think this sample is out of distribution? This is because it lands far away from all the prototypes and doesn't look like the training data. So ML consumers know they need to be careful with the class predictions, and engineers may need to add a new class label. Besides image data, ScatterUQ can also display tabular data. We trained a separate model on a cyber network traffic dataset to demonstrate that ScatterUQ is not just limited to image data. Here, the model believes this test sample comes from a kind of streaming application, and you can compare the test sample with the training examples of the streaming class. In the future, we want to add support for all other kinds of data, including text, image detection, and sound. Briefly back to why we chose PCA. In several experiments, we compared principal component analysis, t-SNE, UMAP, and multidimensional scaling, and quantitatively measured their distance and neighborhood preservation metrics. In the end, PCA outperformed all the other methods in all metrics, including computation time, and we talk about this more in depth in the paper. In conclusion, ScatterUQ is designed to complement distance and uncertainty-aware multi-class neural networks to provide context-driven visualizations for 3 different usage scenarios. And by focusing on local visualizations, ScatterUQ can scale to arbitrarily many classes and data sizes. We have open sourced both the neural network architecture as well as the ScatterUQ visualization web app, and we envision end users leveraging the open source library to enhance their neural networks with uncertainty quantification and to use ScatterUQ to rapidly build downstream visualizations for end users.